Hi everyone. Today's lesson is about systems of equations, and I'm only going to be considering 2D equations, so x and y variable, producing lines in the two-dimensional plane. The reason for that is that I want to focus on the outcome when we solve these equations. And as you can see here from my little diagram, the outcome is either consistent equations or inconsistent equations. If they're consistent, it means they work. There are solutions. If they're inconsistent, it means they don't work nicely together. There are no solutions. Now, in the case of consistent equations, there could be a unique solution, in which case they are independent, or there could be infinitely many solutions, in which case they are dependent equations. Let's get into some examples and take a look at how this works. So to begin with, here is a pair of equations. They're written in standard form with the x's, the y's. Now, I could, of course, write this as a matrix, an augmented matrix, with just the coefficient of x, then the coefficient of y, then the constant term. So I'd have 3, and I'd have positive 1, and I'd have 12. Remember, we put a little line down there for that matrix. I could solve this by pen and paper, but for the sake of being a little bit quicker, let's use our technology. So I need 2, then -1, then 1, 3, 1, 12. I hope I've got that right. And I forgot at the front, I wanted to get the calculator to put this into row reduced echelon form. There we go. And I'll just write that down now. So the reduced row echelon form was 1, 0, 13 over 5, and 0, 1, 21 over 5. So that is a unique solution. The interpretation of this second row is that y equals 21 over 5, and the interpretation of the first row is that x, 1x plus no y's, equals 13. So the unique solution to this one, xy, equals, so 13 over 5, that's 2.6 in decimals, and 21 over 5 is 4.2 in decimals. This, being a unique solution, is the first one up here. Consistent equations, they work nicely together, they do have a solution, and they are independent equations. There is just one solution. Now, as a further illustration of this, let me just use a different piece of technology to illustrate these two equations on our graph here. So there's my first equation, there's my second equation. They both form lines. Of course, 2D makes a line, and where they intersect here is in fact the number 2.6, 4.2, like we solved. So that's the graphical interpretation of a set of independent equations, consistent independent equations. Now, in terms of the matrix, we get leading zeros, and we get leading zeros on the diagonal, and we get, sorry, leading ones, what am I talking about? And then we've got the 0 here. That gives us our unique solution. Now let's try a different example. This one I'm going to go with y equals negative 2x plus 1. Let's call that our first equation. And 4x plus 2y equals 2. Let's call that our second equation. Now I will need to rewrite that first equation in standard form. So this first equation, I'd transpose the 2x, I still have plus y equals 1. And our second equation, I don't need, it's already standard, it's 4x plus 2y equals 2. Putting this in the form of an augmented matrix, I would have 2, 1, 1, and 4, 2, 2. Now you might already start to suspect that something is going to go a little bit wrong here. So let's put that into our calculator and do the calculation. I'll just take out what we had there. Oops, I went too far. I need a matrix there, don't I? Let's go back to put a matrix there, which is a 2 by 3 matrix. Yes, so here we go. My matrix is 2, 1, 1, 4, 2, 2. And look what's happened when we do our reduced row echelon form. Let's just copy that down. It was, the first row was 1, half, half, and this is the bit, 3 zeros. Now, there's nothing wrong with that second row. It means 0 times x plus 0 times y equals 0. Perfectly true. But as we'll see when we look at the graphical interpretation of this, so I'll turn those ones off. Now, that was my first equation there, y equaled negative 2x plus 1. And there's my second equation. Do you see what's happened? The two equations are they are exactly the same equation. This is why we've got that there is solutions. Any point you like along this line is a solution to both of the equations. So these ones are dependent equations. Helps if I can write a little bit more neatly than that. Not much better. And as I said up at the top, a dependent equation is a consistent pair. They do have solutions. That means they're consistent. They work together, but there's not a unique solution. There are, in fact, in this case, infinitely many solutions. The key to that one, when we do our matrix, our Gaussian elimination, is you get this line of zeros. Factually, it is true. 0 times x plus 0 times y does equal 0. But that's a sure sign that you're dealing with dependent equations. And remember, a dependent equation is where one of the equations is a linear combination of the other equations in the system. And in our case here of 2 by 2, equation 2 is just 2 times equation 1. So it's pretty straightforward. You would have spotted that, I'm sure. Can be more difficult to spot in more complicated systems. Now let's look at a third example. Y equals negative 3x plus 1. There's our first equation. And then I have 9x try that again, plus 3y equals 12. Second equation. First one needs to be written in standard form. So I'll transpose the 3x plus y equals 1. And my second equation is already standard form, 9x plus 3y equals 12. Once again, we'll go for Gaussian elimination, 3, 1, 1, and 9, 3, 12. Let's go for our calculator. Once again, in this simple case of some 2 by 2 equations, you may already start to suspect that something looks a little bit off here. So I've got 3, 1, 1 for the first equation, then 9, 3, 12. And look what's happened in my solution there. I'll just copy that down for you. We have 1, 1/3, 0, and the second row this time, 0, 0, 1. Now, look at that second line. That's telling me that 0 times x plus 0 times y equals 1. Effectively, that second equation says that 0 equals 1, which is complete rubbish. 0 cannot possibly equal 1. This is a huge, huge red flag that these equations are not playing nicely together. These are consistent. Okay, the previous two were both consistent because they actually did solve, but this one doesn't solve. Now I'll show you what I mean on the graph. I'll take those ones away. So here's my first equation from this set, y equal negative 3x plus 1, perfectly good equation, lovely. Now here's the next one. You can see what's going on. We've got parallel lines here. These parallel lines are never, ever going to intersect, which means you will never find a value that satisfies both. That's what we mean by inconsistent equations. So when we get something that looks like this, it's a sure sign that our equations are inconsistent. Okay, thanks for watching. See you next time.